bird. It's a plane. No, it's a Zephyr? The gentle, soft breeze on the west wind? No, not that. The iconic rail line down the western coast of the United States. Nope, not that either. Okay, this is Chalk Talk after all. Of course, we are talking about the modern, scalable, real time operating system designed for resource constrained embedded devices. Did you know that Zephyr recently turned 10 years old? It's true. Seems like just yesterday that I was talking about it for the first time here on Chalk Talk. Well, folks, let's dig into the latest and greatest about this collaborative open source project building secure, scalable RTOS connected embedded devices. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Brendon Slade from NXP and I explore what makes Zephyr unique, how it compares to other RTOS options, and how its design philosophy enables developers to scale from simple prototypes to production-ready systems with confidence. And before we get started, don't forget to click that link. There you can find even more information about this topic from NXP. Hi, Brendon. Thank you so much for joining me.
Oh, it's great to meet up with you again, Amelia. I've been looking forward to this conversation.
Me too. All right, so we're talking all about Zephyr today and the momentum driving its adoption. And Brendon, Zephyr is now 10 years old, right?
Yeah, that's right, Amelia. 10 years old this March. I can't believe 10 years has flown by so quickly from the 2015 origins of the project. So this picture is actually a Zephyr cake. I didn't know about Zephyr cakes till I started looking for a nice one for this presentation. And there's a Zephyr cake made of meringue. It looks pretty good, right? But now, yeah, 10 years in, there's a huge wave of momentum behind Zephyr. So today I'm hoping to give some insights about what's happening and why that's happening. So some of the listeners might be thinking, isn't this just a more complicated RTOS? They may have seen that on social media and discussions and so on. But I want to clarify that common question by digging into more of the layers of our cake to see what's rather tasty on the inside when it comes to development.
Fantastic.
Leading on from that, Zephyr was ticking along for about 5 years, growing from its roots and incubation period. And then the COVID pandemic hit. And as we all know, this created a massive supply chain crisis that impacted everyone from the suppliers like NXP to all our customers. And customers just couldn't get the devices they needed, the ones that they'd been taking for granted for years in various different designs they had. And many companies had very disparate designs across their different product lines and so on. And they were left scrambling to try and find alternatives from their suppliers, or even to look for completely new devices from new suppliers to get products out the door. And as companies got out of this kind of disaster mode and started to recover from those times, they started to think more strategically about the long-term benefits of moving to an RTOS that gave them more portability. And that's really where Zephyr started to become more attractive.
That might explain the trends that I've seen lately that point toward code portability and desire for configurability without code rewrite. Is that what you're seeing as well?
Yeah, we definitely seeing the customers want to reuse their code bases more and more across their product lines and have that robustness against supply issues. So the portability of Zephyr is really critical to making them consider that option. So when you compare Zephyr to other RTOSs, it's often described as more complicated, mainly because of the concept of device trees that originates from Linux. So a Linux developer is going to be very familiar and comfortable with this, but for MCU developers, it's a bit scary. But what it really does is enables you to link a device driver to particular hardware. So if I'm working on device A or device B, I use the device tree to bind those things together. And then I don't need to touch my source code to make changes, which is different from traditional RTOSs and bare metal implementations. And beyond that device tree hardware mapping, you also have a concept that also comes from Linux, which is kconfig, which enables you to define the software features you want or the parameters of software features in a single configuration file and build it. So again, no messing around with your application code, provided it has some notion of those configuration options. So once you get over that slightly scary learning curve, the porting process becomes very fast and efficient. There's other things that come along with it, like continuous integration and test is kind of built into Zephyr. It brings these cool things, Z-test and Twister, that enables you to have an automatically set up test infrastructure, run a tool that is in Python, enables you to grab tests and run them easily and leverage a lot of what's already in the open source. And that was a great contribution from Google.
So there is this portability component, but treating Zephyr like a traditional RTOS really sells it short, right, Brendan?
Yeah, it definitely does because, there's so much more to Zephyr than just the RTOS, which is at kind of the heart of it. And people they see RTOS in the microcontroller space. Oh, tell me the context switch times and various other things. So then they'll start looking at things like the footprint, the schedule performance, raw efficiency. And compared to other RTOSs, Zephyr does fine. It's not the fastest, it's not the slowest, it's very comparable. And it's not as big as some people think, because some people think they hear device trees and kconfig and they say, oh, it's just like Linux, right? It's just Linux from microcontrollers, so it must be huge. But that's really not true. We're talking about a change from times when firmware was very small and self-contained. You just wanted to keep things simple and really small. But now there's so much more that's expected from a microcontroller. Things like networking, security updates, power management, diagnostics, dealing with very long product lifetimes. So Zephyr can feel a bit more complex because it has this infrastructure built into it up front. A lot of things you'd have to kind of figure out how to bolt on manually are already there, but then that means when you get the product out of the box, it's inherently got more complexity to it. Just reiterating some of those points. So size-wise, Zephyr is very close to other popular RTOSs once you set the settings to be comparing apples to apples, right? So a lot of stuff in Zephyr comes turned on out of the box. The things like stack checking, which you need for safety and security. Other RTOSs don't have that, or it may not be enabled by default. And that costs you performance and size, but it's a trade-off people quite often need to make. There's that configuration-driven portability, describing your hardware with the device tree and software with kconfig. A little bit scary, huge benefits for portability. And then there's that automated test infrastructure that comes along as continuous integration and test becomes critically important, especially for bigger projects with a lot of engineers involved. But then the thing that I haven't mentioned yet is critical is all the middleware that comes out of the box.
All right. So, Brendan, can we take a look under the hood and see what the architecture of Zephyr really looks like?
Yeah, absolutely. So let's look at this picture and start at the bottom and work our way up, because that's really the key to understanding Zephyr. So at the foundation is the platform layer. This is where the silicon specific details live, the CPU, the memory, interrupts, basic hardware bring up. And sitting just above that are the power management and kernel services. Zephyr does have some nice things for power management, so it's more portable because devices can be different in terms of how they handle that, and it unifies those things. But this is still the real RTOS core: scheduling, threads, synchronization, timing, all that. Very familiar territory if you used any RTOS before. Above the kernel, Zephyr provides this rich set of OS services, things like serial and peripheral drivers, file systems, logging, settings, crypto. These are integrated, configurable, and designed to work consistently across platforms, once again. And on top of that, we get the connectivity stacks and application services. So networking, protocols, device management, everything that kind of modern edge connected secure device needs and is expected as a table stakes. And this is where that richness of middleware really starts to come in and will be a real good thing for people to see of other things they haven't got to go and collect from other places. And finally, at the very top is the application. And the important takeaway is that Zephyr lets you consume as much or as little of this stack as you need, while keeping clean separation between hardware, OS, and application logic. So just because there's a lot of stuff in this stack, it doesn't mean you need to include it all in your application. You just choose what you want, which is kind of what microcontroller software development is all about, optimizing what you need for your particular application. And all of this comes along with this great portability, scalability across different devices, and long-term maintainability is a very well-run open source project.
So, Brendan, let's talk more about scalability. It's a central aspect of Zephyr, right?
Yeah, it is. And for NXP, it's one of the great things about Zephyr because NXP's got this very wide range of microcontrollers, ranging all the way up through crossover processors into the IMX microprocessors. And all of these can run Zephyr. So for us, it really enables our customers to utilize that scalability. But coming back to the more general case, Jacob Benengo, I quoted him here because he sums that up really well. And this was a response from a survey the Zephyr project did just for the 10-year anniversary. But he's saying it's all about avoiding just doing the same work over and over because you've switched to a different processor. It allows customers, engineers to move quickly and focus on the value add and not just reinventing the wheel again because I've moved from this processor one to processor two and having to redo all those things. The value add in productivity and ability to move quickly is really pretty huge for the customers.
We talked about portability earlier. So, how does this design concern fit into the NXP ecosystem as a whole?
If you look at an example here across a couple of NXP's processors, I mentioned crossover processors. What we have here is the IMX-RT family, which was an innovation NXP brought in probably around 8 or so years ago now. This is the concept of taking an IMX processor and reusing it for a microcontroller. That means there's no on-chip flash. The peripheral set is a little different. And then we're comparing it to a more traditional flash-based microcontroller like the MCX-N here. If you try and port code between those two, it's challenging because the memory systems are different, the capabilities are different, and the drivers are different. So it's quite a challenging thing to do that kind of code porting in a traditional sense. Even if you have a hardware abstraction layer, it's not the easiest thing to do.
So, do you have any examples of real world designs that you can share?
Yeah, I'm glad you asked me that because I have a great demo right here. So this is a face detector using AI. You can see the two different screens are slightly different. The two platforms we're talking about are very different, as we just saw in the last slide. But yet this is the same application code running on both of these products. The MCXN is running at about 150 megahertz and it has a hardware NPU, whereas the IMX RT1060, which is the other board on the right here, that has a Cortex M7 core running at very high speed, running at 600 megahertz. Now, to utilize that NPU, you would think that's going to be a difficult challenge. And how can I make the same application run efficiently on that? But the layers within Zephyr enable you to do that mapping very easily. And again, don't have to touch your application code because we're using a TF Lite model here, and Zephyr can map that down to the underlying hardware. And NXP's enabled those interface layers in the upstream to do that. So it's a combination of the hardware abstraction layer enabling you to use the applications through a standardized API down to very different hardware interfaces, and the TF Lite support in Zephyr being able to map that AI model down to those two different hardware capabilities very efficiently as well.
So, Brendan, can we walk through those two hardware architecture differences you mentioned a bit more?
Yeah, definitely. So if we compare the two platforms, we can see several differences in the peripheral IP. The camera interface uses a special smart DMA feature plus GPIOs on the MCX device. It doesn't have a native display, but the RT1060 has a MIPI CSI interface, which is a standard interface. So they're quite different implementations. On the display side of things, the display interfaces are also very different, with the RT1060 being able to drive an LCD panel directly, while the MCX device can either use a SPI interface or an implementation of a parallel LCD interface, which uses our specialist FlexIO accelerator block, which is very flexible in what it can do. But porting the application does not require recoding of any of these drivers. So we can see that here, back to the Zephyr architecture with a bit more detail at the bottom end. You can see as we drill down, there's lots of details here on the exact IP blocks and drivers that we have. And down at the lowest level, you can see all the differences in the hardware, all those display drivers, cameras, etc. that I just mentioned. After that, there's NXP SDK drivers, which is NXP's MCU Expresso SDK. And on top of that, we have this interface or shim layer that translates to the Zephyr standard HAL. So now at this point, at the Zephyr standard HAL layer, you've got an interface that would look the same for our devices or Infineon or ST or Nordic, whatever they might be. So that's one level of portability. And then the device tree, as I mentioned earlier, is then used to bind those drivers to the specific application. So in some cases, in a different case, you might want to, support display through another interface. And if a device has more than one option, you can use the binding to choose the one that's most appropriate. And then kconfig is used to configure things. This is how we deal with things like the fact that display is landscape on one, portrait on another, and the resolutions are different. So kconfig enables you to do that in a standardized way. So again, you don't have to hard code things in the application itself.
So 10 years ago now, what motivated NXP to get involved in Zephyr in the first place?
Yeah, good question. I mean, it really came down to three factors. First, NXP and some of the other co-founders were anticipating that the microcontroller market could follow the trend we saw about 15 years earlier with embedded Linux and microprocessors, where a lot of it was driven by things like Android adoption, but there was this very rapid transition over the period of about 5 years to using open source OSs like Android and Linux. Now, with microcontrollers getting more capable and applications getting more complex, there's more and more features that had to be managed and supported. That gave more reasoning that this was likely to happen. Because if you look at embedded Linux, has this massive library or collection of drivers and capabilities that have built up by way of there being an open source project to focus them on. And that wouldn't happen if you had all proprietary OSs. So we figured that microcontrollers could go the same way. We chose Zephyr for this because we felt that the goals of the project align very well with NXP's, which is where we see a world of edge connected devices that all have to become smarter, safer, and more secure. And the third reason may not be so obvious, so let me explain that in a little more detail. Why would a company like NXP work on a project where we potentially would lose stickiness? Traditionally, it's been the case that you provide software and it's difficult for customers to move. As things get more and more complicated, that becomes a bigger and bigger burden for a company like NXP and any other semiconductor vendors. It comes down to technical debt and the reduction of technical debt, where there isn't a clear differentiating value for us. But it's also on a more altruistic side, we want customers to be successful using the hardware capabilities of our parts. And if we didn't work as a community to make all the boats rise on this tide of collaboration, then the customers just would never be able to get to solve those problems in a cost-effective way. Also related to that, it's about customer support, because if customers can't solve their problems in these more complex software systems, they don't get to market, they don't get to revenue, and we don't get to revenue. So it's a synergistic thing. By sharing this effort with some of our frenemies in the semiconductor market, we're really helping our customers and helping ourselves.
So there are a lot of companies than just NXP involved in Zephyr, right?
Yeah, now it's somewhere around 57 members. I mean, it's changing so fast. That number might be out of date by the time we get this recording out. But yeah, new members are coming in all the time. But one of the things that's really important to realize is that you don't have to be a member of the project to contribute. In fact, some of the maintainers in the project are from companies that aren't members. So it's all free for anyone to use, and you can get involved without being a member. Being a member really gives you more influence on the priorities of the project and where the funds that come from membership fees get invested, but it's open to everybody. And one other comment, if you look at the members, it's not just semiconductor vendors. It's very much not the case. There's a mix of software companies, training companies, and most importantly, OEMs across various different markets. So that kind of diversity really ensures that it moves forward in the right way. So I hope that's given you a good insight, Amelia. I did want to just add a few kind of takeaways and next steps for people who want to find out more information, including this link to a great resource from Mauser about what NXP has to offer in the field of Zephyr. I'd encourage people to look at zephyrproject.org as well to find more about the greater project goals and device support and so on.
Absolutely. This has been fantastic. Thank you so much for joining me, Brendon.
Well, thanks so much. It's been a real pleasure. Always is fun talking to you, Amelia, and thanks for the great questions.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from NXP. For Chalk Talks, I'm Amelia Dalton from EE Journal. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.